Victor. Oh, no. Oh, yeah. The meeting is being recorded. Yes, thank you, Alessio. The meeting is being recorded, as we usually do, so people can also watch it later. So Victor, he is the leader of the Climate Biosphere Interaction Group at the Max Planck Institute for Meteorology here in Hamburg, and he is also associate professor at the University of Hamburg. He has also done work at, or was a research scientist at PIC, the Potsdam Institute for Climate, and he was also working in different countries over his career, and his particular interest is beyond what he is presenting, of course, today, is the biosphere and the interaction between biosphere, land, atmosphere, and complex systems. So I welcome you here with this webinar. I'm really pleased to have you here and giving us an overview about tipping points. You can share your screen if it's possible.
Yeah, thank you, Jana, for the introduction. Yeah, I can start sharing. Can you see my screen?
Yes.
Excellent. Just do it in full screen mode. All right. So, as Jana said, I'm leading a group in Max Planck Institute for Meteorology in Hamburg, but I also, for several years, I was a leader of AIMS analysis, interpretation and modeling of Earth system project of Future Earth. And we had a meeting together with PAGES, so that is past global changes, also part of Future Earth program. We wanted to see how and what happened in the past with abrupt changes. And we also thought about cascading of impacts in the Earth system. And just want to start with this information. So the issue is that if we go to the past, then geological records are really full of abrupt events. And if we look at this particular Greenland ice core record, so you can see that there are a strong fluctuation, particular if you go here from the right to the present day, so that then you can see many spikes, which were later associated with changes at Atlantic meridian overturning, and I will talk about that in details. But the issue is that past is really what have happened. We don't know what will happen in the future, but from the past we can think about analogies and what could actually be in the future. And because we have a very long history of our system, so hopefully Earth doesn't go through a runaway effect, but we know what could happen when the temperature crosses this or another threshold. And this is very important for us also to look into the future. If I go to the next slide, so I just have first want to go through history of tipping points research, because it started at PIC a while ago, then go through definitions, because definitions are important when we talk about abruptness. Examples of abrupt changes, I will focus on onset of Belling-Allerød warming associated with changes in MOC, Atlantic meridian overturning, and then also talk about hydroclimate instability in the Holocene or mega droughts. Then just briefly, I will talk about early warning signals and then give a perspective. So regarding tipping point, for me, everything started with dynamical system theory, and probably the first really relevant to the Earth system was Boudica-Sellers model, which showed that ice albedo feedback could really lead to two different states. So the present state of the Earth plus snowball Earth. And then also, of course, many of you know that in the Atlantic meridian overturning, there is also multi-stability. And it is, if you look here on the left side, there is the strength of this multi-stability, circulation in terms of Sverdrups, and here freshwater flux to North Atlantic. And there is a hysteresis in a way that the stronger the freshwater flux, the stronger is a probability of collapsing of circulation. And at some point, there is no circulation at all. And when just to go backward to restore circulation, we really need to go, through the whole hysteresis back. So going through this black circle. What is also interesting that it was an example from the ocean, but there is also example from vegetation, and in particular due to interactions between vegetation and climate in North Africa. So not everyone knows, but in the mid-Holocene, about 6,000 years ago, Sahara was much more greener than today. So there was the work of Martin Clausen and Veronica Geile on that already more than 20 years ago. And actually, when we go to present day, so we see that, it's possible to have two steady states. One is the desert Sahara as we know it now, but it will be as a possibility for vegetated Sahara state, shown in the couple interaction between vegetation and climate. So this is also a feature of multi-stability, and that's important to understand how this concept comes in. But tipping point concept is not just about multi-stability or bifurcation. It is more about also, on one hand, it's the system may have different steady states which become stable or unstable, but it's also about the differences and non-linearity. So after crossing some threshold, the system can change quite quickly. And then because there are some connections between components of the Earth system, it could be impacts of one tipping elements on another one. And all these abrupt changes were occurred in the geological history, so they could happen again. That's why we are interested to learn from them. And this is a quite well-known paper by Tim Lenton, so about possible tipping elements in the Earth system. So there are in particular features, for example, here, the Atlantic deep water formation, dieback on Amazon rainforest. Just I think this week there was a paper in Nature Climate Change about possibility of dieback of Amazon rainforest increasing. And then there are some others which are also possible with multi-stability. But when one look at this map, in behind just a background, we use a population density map. So we wanted to see where exactly changes or tipping of a system could lead to strong effect on population. And I think Indian monsoon, and particularly here West African monsoon shift and Sahara greening, that's probably where the most humans will be affected if there is some abrupt changes. And in that paper, the term tipping point was introduced as a critical threshold at which a tiny perturbation can qualitatively alter the state or development of a system. So it is not multi-stability, it's not a bifurcation, it's just threshold after which there is a strong non-linearity. And the term tipping element describes large-scale components of Earth system. We also can think about much smaller components of Earth system, pieces of Amazon forest, for example, which could also change non-linearly if a forcing is changing. But that's rather more modern development of this tipping elements theory. It is important then to define this terminology, and that's what is from the recent IPCC A6 report from Working Group 1. I hope that it is consistent with Working Group 2 and 3 for IPCC. So they define abrupt change as a change that is substantially faster than the typical rate of changes in its history. So here we have a reference. So there is a history and there is a present, and we see that now there is a substantial acceleration of something in the system. So that's definition of abrupt change. But for climate change, we actually use another definition. So this is abrupt change on large scale that take place over a few decades or less. So here it's time scale is important. And there is, of course, definition of irreversibility. I think that's would be in line with mathematical theory too, that is perturbed state of a dynamical system is defined as irreversible on a given time scale if the recovery from these states due to natural processes takes substantially longer than the time scale of interest. So basically, recovery takes much longer than a usual time scale of processes. And by tipping point, IPCC understand a critical threshold beyond which a system reorganizes often abruptly or irreversibly, but it's not necessary with irreversibility. And tipping element is a component of Earth system that is susceptible to a tipping point. So it doesn't say again about the scale, but presumably component should be of the Earth system should be quite large. If one do paleoanalysis of the past changes, it is important to know what is relevant. And for past, of course, abrupt can be defined differently. And generally, it is viewed as in the previous IPCC report that it is large-scale change that is much faster than the change in the relevant forcing. And in that case, in the paleo content, the relevant forcing is usually the orbital forcing, and it has multi-millennial time scale. So principally, everything can be faster if it's faster than the forcing of changes in the Earth orbit. And then there is also a definition of cascading impact. So it is a sequence of events when abrupt changes in one component lead to abrupt changes in the other components. So it can be interaction or it can be just cascading of impact. So it goes just from one component, let's say something changes in meridional overturning, and then we see how this goes over all domains of the Earth system. Now just come into examples. So if you look at again at the oxygen isotopic record, you can see that there are many abrupt events, so-called Dashka-Urge events, and there is also Belling-Allerød onset. So it happens about 14.7 thousand years ago, when suddenly there was a strong warming. So it is from Greenland. So in Greenland, it was over a few years, the warming was on a scale of about 10 degrees. At the same time, there was also surface warming in North Pacific. There was, after all, there was a rapid ice sheet melt, acceleration of sea level rise in response to that. But also, it was changing in hydroclimate. So there was dryness in southwestern North America. So West African monsoon intensified while South American was weakening. And it's also affected the ecosystem. So there was rapid afforestation of tundra in Scandinavia. Species were coming out of glacial refugia. Diversity. And last but not least, there was also abrupt changes in atmospheric methane and CO2. So I guess it was small interruption, but I just want to go into figures, or just to show really in the records how it looks like. So if you go to origin of changes, so this abrupt changes in MIC, that we think is important. Here at the top, can you see my cursor? Hopefully, yes. Okay. Then, yeah, around 14. So this bar indicates a change in meridional overturning. So it was suddenly much stronger. And when in response to it, you can see that in North Pacific, so far from this place, there was changes in hypoxia at the bottom of the ocean. Also, there was relatively abrupt sea level rise. And if one look at the CO2 record from the ice core, there was a substantial increase of about 12 ppm within several decades around this period. And at the same time, there was a methane. Methane is usually responding much faster to warming than CO2. And well, one can also find records which show that there was also strong increase in tree cover. So all of that happened around this Belling-Allerød warming. So it was really abrupt event. So I can think that if there is something happening and North Atlantic circulation restores or just jumps over certain threshold, then these changes are propagating from physical climate system to ecosystems, and then presumably to societies. It's just that we don't have society paleo records for 15,000 years ago, but one can follow it if there is a change in MOC, then, well, in the ecosystem, this means hypoxia in the ocean, and this definitely would affect the fishery, for example. There is change on land, so water is becoming more available, vegetation responds to the warming, but because of the sea level rise, there is also loss and flooding. In particular, there was a strong flooding on the Arctic shelf at that time, and society should respond to that. So it should also be migration, adaptation, and moving of coastal settlements up from the sea. And this, in particular, this MOC change could happen quite abruptly. So that was really interesting in this example. So that can happen on the decadal scale, while cascades were, of course, going slower. And the quality and precision of geological record is not good enough just to say how long exactly was this period of changes. Another event I want to focus is changes in hydroclimate. So if you now go into the period from in the Holocene, or was, you can see here a slight spike when there was a Holocene onset about 12.7 thousand years ago, and then there was also, if you want to talk about catastrophes, there was Black Sea flooding, because there was a period when the salty water from Mediterranean Sea just due to sea level rise went over the seal of Bosphorus, and then there was over several decades or perhaps century, there was the flooding of the Black Sea, and there was really catastrophe for population which was living on the coast at that time. And when there is in the period I want to talk about Holocene aridification in Africa, and that happens about 8 to 3,000 years ago. There was no precise record when exactly it happened, but what is interesting that all proxy says that there was decreasing monsoon rainfall in North Africa, and also the same was happening in mid-continental North America, and we can see that in shifts of North American grasslands and also activations of dune changes in C3 to C4 plants, and also this is recorded in the fires. One other variability is Holocene mega droughts, and the mega droughts is usually defined as droughts which are really exceptionally long, so go for decades and so on, so that people don't really have chance to respond to that, because the whole system might collapse in response to that. And we see that in response to these changes, there was change in tree growth rates, abandonment of early agricultural sites. So in the original paper, we have all references if they are of interest for this site. And just one more to show this period. So I think the kind of canonic record for it is for heterogeneous dust in North Africa, or from the coast of close to the West North Africa. And there was increase within few decades of heterogeneous dust from about 45 to 60%, really abrupt. And one can also see droughts later periodically in the area. So here, one record of drought, I think this is from area close to Ethiopia, and there was also in Asia drought event in Angkor, but that's already in the last millennium. So there was these aridity events that really affect the whole system, and at that time there was already settlements, so there were also strong effects on population. So we think that when these events are coming, so we have slow changes in orbital force, and they shift monsoonal rainfall belts, and this leads sometimes to abrupt, sometimes to more smooth desertification changes in aquatic terrestrial system. And it was also affecting the, for example, the flooding on the Nile River. And that should have lead to substantial changes in pastoral societies and also to dynastic turnovers in Egypt. So there was several papers dedicated to that. Now I want to say how to measure abruptness, because how abrupt is abrupt? It's not easy to define. So as I mentioned before, there are several definitions. So we use two definitions in our paper. One is ratio of abrupt to reference period, right? So let's say we have some record here, so of heterogeneous dust. So there is this is a decrease in the increase in the dust during the reference period. So we see it's quite slow. And then there is a period of change, and then again there is now a new state. So you can see that you can define abruptness of changes in reference to the previous period, and that's, I think, one of the also definition which IPCC takes now for abruptness. And second can be as a ratio of abrupt to orbital forcing changes. So I just put here on the same scale the changes in summer radiation, so you can see that indeed changes in dust are much faster comparing to radiation changes. And if you just define that, we can also go and for this particular record, we can just define the period of abrupt change, see how strongly the change is, and then define the rate of changes during abrupt period, during the reference period, and calculate the ratio of abruptness relative to the reference periods. And for example, here it's about 20. And if you do the same for the orbital forcing, we also come to the roughly same number. So actually, whether you define in one or another way, results are not much different. So during the abrupt period, the changes are about 20 times faster than before. Just one example from societal systems. So there was also, this is a drought index, and this is the last millennium, and that's in the Asia, that is this drought was associated with a collapse of the Khmer Empire at Angkor, and there were several investigations what could happen, and one of the reasons is that the drought was so strong that the social system collapsed because it was already vulnerable because it has a hydrology system, but during that period the system was overextended, and vulnerability was so strong that the whole empire collapsed. Just next point is on the early warning signals. So some of you know and already are aware about these qualitative indicators of proximity of a system to a tipping point. So it's kind of mathematical analysis of time series, and for example, increase autocorrelation variance before abrupt change, so-called slowing down, is an example of what we can call early warning signal. And one of the paper where we were introduced was from Vasilis Dakas in 2008. So here there are two examples. So one is it's geological records. I think one is Belling-Allerød transition, and here you see the temperature. So again, it is a proxy, I think 018, but it can be introduced, interpreted in that way. And if one look at the autocorrelation, one can see that autocorrelation, well, it's not immediately increasing. There is a lot of noise, but there is some increase in autocorrelation in that period. And if one take the record here on the right for the dust, so which I mentioned, and then focus on the period of this abrupt change, when prior to this period there is increase in autocorrelation, so which also might be interpreted as loss of stability in the system. And of course, the geological records, so you can interpret them in different way. But if you have a model, you can really look into details of it. So we also had a coupled conceptual model of interaction between vegetation cover, so here the y-axis, and precipitation via albedo changes in North Africa. And with this model, one can get also hysteresis. So just at present day, we have only one state, which is desert, and before that, around 8,000 years ago, the only stable state was Green Sahara. And there is here the hysteresis lupus often in this dynamical system when we have two equilibria, just one above and one below. And if I'm looking autocorrelation, so it is increasing just in the model. So it's again the model, so model might be not as informative as the data, but that's all what we can have. And that's actually supporting material for analysis of time series. If you talk about this early warning signals or precursors of abrupt changes in the Earth system, one can think about univariate precursors, so like autocorrelation, but there are also spatially explicit precursors, such as pattern correlation. And if I start to analyze the literature, what's going on with these precursors for DO events, when there is no agreement in the literature. So one group of authors argue that it is noise-induced shifts, so it shouldn't be early warning signals, but some says, well, there is still increase in autocorrelation variance, but not for individual events. And some really see increase in autocorrelation on decadal timescale preceding events. So there are different groups which are discussing. I'm not actually involved in this discussion, but there is also for African human period, there is no clear view whether there is early warning signal for end of African human period. What is interesting for this vegetation system is that there is a vegetation pattern formation in drylands, and one can argue that just before the collapse of vegetation cover, there is a change in vegetation patterns. So there is also increasing spatial variance and skewness in simple model. So one can also look at the patterns and think whether there is a signal there of changes in the state. And there was also analysis of social collapses and transformation. Also, people looked at the increasing variance in autocorrelation before population collapse in Europe, in Neolithic, or in social transformation in pre-Hispanic United States Southwest. And I also want to point that this pioneering study by Heldet Kleiden, done actually at PIC, where they show that autocorrelation is a possible early warning signal. That's now, I think, cited in every paper which published on early warning signals. So for perspectives, so that's what we did. So what one observed in the data, but what could be an outlook? What can we do with paleo abrupt changes? And one of the things which we need to improve is precision and resolution, also reproducibility of paleo records, because of course now there is a better technique with mass spectrometry. There are many excellent time series, and we need that for identifying early warning signals. And with increasing precision, the chance for identifying becomes better. Then of course we want the synthesis of data, because they are in the different domains of the Earth system. So they are in cryosphere, they are in hydrosphere, or in biosphere, and we need to look at different aspects of it. And of course, one of a unified framework is Earth system models. And here, of course, the remark is that current subgrid scale parameterization in Earth system models, it's rather simulates gradual changes. And we hope that increasing model resolution and improving subgrid scale parameterization is a way to go to just to find more and more abrupt changes when we go for Earth system models. Just very, I just also want to say perspective that now, of course, it's not about paleo, but we also now have a huge data set of remote sensing, and one can also think about multi-stability in this system. So here, one study that we did a while ago with Benjamin Abis in our group, And here we look at the distribution of vegetation cover, in particular in forest. And when we check up the sites where for the same, absolutely the same environmental conditions, we can find forest or open woodland or treeless cover. And when we saw that about 5%, so here indicated in this bluish color, where these areas tends to have to be multi-stable. So for the same condition, they can have different states. And of course, if there is some change, like there is a disturbance, fire, or insects outbreak, then the system can change from one state to another. So it will be also abrupt changes, but scale is here much finer. So you see, it's not the whole Amazon, it's not the whole boreal forest, it's just small, rather small patches, but that's also what is relevant for risk and for policymakers, because we really need to go to finer scale. I think that's coming to the end, and I just also want to make announcement. Many of you know already that there is AIMS, Earth Commissions, and WCRP. They have webinars on tipping elements, irreversibility, and abrupt change in the Earth system. And the next one will be on 7th of April, and it will go into interlinkages or connections between Earth and human systems. And it will be about dust bowl and the case of small island states. And yeah, there is also a project of Earth Commission on tipping point model intercomparison. So just analyzing where exactly can we get in the models with tipping points. And yeah, with that, I'm ending, and that's just a picture of our workshop participants almost 4 years ago, but it was time before Corona, so we could meet in person and then actually did the science together. So hopefully we can do it soon again. Thank you for your attention.